We are a car, but we've got the complexity of a jet fighter attached to the top of it, a rocket inside it, and a Formula 1 engine.
We're going to be the fastest thing at ground level, faster than a jet fighter. So we're going to set an airspeed record as well.
Everybody intuitively understands that this is staggeringly difficult. We're engineers, and even for us, occasionally, we look at some of the data points and we have to shake our heads.
We've got a car with a Union flag on the fin. We are promoting great British engineering on a global stage and showcasing what we do absolutely brilliantly well in this country. And of course, here we are at Autosports, guests of the MIA on the motorsports stand, and we are showcasing the 9,000 companies they've got working for them and all their capability. A lot of those companies are going to be making bits of the car. It's a very exciting opportunity for us.
There was a meeting with the UK Trade Industry Board, and they realised we had a shortage of engineers, and they needed to find a way to encourage young engineers, and that was seen to be a land speed record car.
We are a land speed record project, but breaking the land speed record is pretty much number 3 on our agenda. Number 1 is to inspire the next generation of children to think science is exciting, challenging, fun, maths is great. Second is to generate the stuff going in the curriculum, so to make all our data available. We're open source, you can go on the web, you can download our engineering details, our data, and really provide stuff for them to use in class and school. And number 3 is to break the record. And number 4 is to promote UK PLC, fantastic engineering, give all the support we can to people that help us, the product sponsors, and give a real lift.
Bloodhound SSC is the next land speed record attempt. It's being done by a team of British engineers, and we're aiming for 1,000 miles an hour. At the front of the car will be mostly constructed using composites, so there'll be a composite tub that's similar to F1 builds. That will continue down past the cockpit, so this is where Andy will actually be located when he's driving the car, so this is his office, if you like. And then you move down, the composites will end just behind the jet intake. And this is where you'll then move into the aluminium space frame, which is very similar to the construction of an aircraft. And within this part of the car, this is where the jet engine will be housed. So that will take us up to about 200–300 miles an hour, and then the rocket system will kick in. So the rocket will be located at the base of the car. And in order to be able to fuel that, we've got a Cosworth F1 engine to drive the pump for the HTP fuel for the rocket system. Well, at the rear of the car, this is the exhaust for the jet engine, but it's also the back end for the rocket. So this is where all of the flames and the big amount of thrust will happen. And also at the back of the car, you've got the wheel fairings. So this is where the solid aluminium wheels will be on the rear end of the car. The sort of speeds that this will be rotating at, there's no need for rubber or anything like that. They need to be solid. We're producing forces of 15,000 radial G at the rim. You know, rubber's just going to disintegrate straight away, so they have to be solid aluminium. It's not a very pretty shape at the back. You know, we've had a very sleek design in the past, but actually doing all the research on it, that creates a lot of drag and a lot of lift. So yeah, this is the perfect sort of shape for what we need. This show car we've had now for a little while, and we've done a lot of research into the fin now, and it'll be about 2 or 3 times taller, and the start of the fin will actually start just behind the jet intake. This is a mock-up of the canopy for the cockpit. Before we put it into manufacture, we have to check, you know, that the windscreen's going to be big enough, and obviously he can get in and out with ease. Well, this is a view that he will have out of the front of the car, and obviously it looks quite small, but he's only trying to follow a black line down the desert. He's just going to try and keep it on a straight line, so this size windscreen's all right for what he needs. This is an example of the type of material that will be used within the windscreen. It's toughened perspex. Obviously, you know, we're travelling along the ground, but there's still the threat of bird strikes. Literally, the whole run will take 90 seconds, and that will cover about 10 miles in 90 seconds.
South Africans are preparing a track for us, 20 kilometres long, it's 12 miles long, out in the middle of the desert in South Africa. They're clearing 20 million square metres by hand to make sure it's a perfect track. It's our first world record, biggest surface area anywhere in the world cleared by hand. We will run 2013 on the world's best racetrack in South Africa. So as long as we can keep the car on the ground, so we can solve the aerodynamics, as long as we can keep the pointy end forwards, shiny side up, and that's just basic sound engineering, then fundamentally the car and me strapped inside it will be safe. Specifically, what's that like for me inside? It's going to be very noisy. I'm sitting, the cockpit's directly underneath the jet intake. The cockpit ramp is actually part of the intake system. The shockwave off the cockpit smooths the airflow into the intake. That means I have to sit directly underneath the jet engine. It's going to be noisy. It's going to be very hot because I'm in a desert, small cockpit, thick fireproof suit, high vibration, and of course the acceleration. Accelerating at over 2G. That's 50 miles an hour per second of acceleration. 0 to 50 in 1 second, that's pretty brisk. When we shut the engines down, the aerodynamic drag will slow the car down at 3G. That's 60 miles an hour per second. If you can imagine, don't try this at home. If you can imagine driving at 60 miles an hour and stopping in 1 second, yes, to most people that would involve a crash. That's what the car's going to feel like. So it's going to be uncomfortable. But apart from all those things, it'll be fine.
The vehicle has to be safe. Basically it's a benign aerodynamic shape. No lift, no downforce. So it's not relying on active systems to keep it on the ground. The car is going to be on its wheels at Christmas this year. We aim to do some low speeds runs around Easter next year. Following on from that, to the middle to the third quarter of next year, we'll run on to the high-speed runs in South Africa up to around about 850 miles an hour. And then the following year we'll go back with any changes that we need to make, and we'll go for the 1,000 miles an hour average speed.
Andy Green, our driver, is the current land speed record holder at 763. So I think it's the world's largest percentage jump on the land speed record, and there are two reasons for doing that. It has to be challenging. It has to be, 1,000 miles an hour is difficult. You can't just take a 763 mile an hour car, look at it, make it a bit quicker, and we could have gone for an 800 record. This is going for 1,000. It's a very, very different shape. We're using a lot of different technologies. This car has 3 engines. It has 133,000 equivalent brake horsepower. If you stood it on its tail and aimed it up in the sky, you get to 25,500 foot and break the sound barrier at 17,000 foot. It's a phenomenal vehicle.
There are currently 3 or 4 other teams out there that are looking at either to break the current Thrust SSC record or to go for 1,000 miles an hour. And actually more competition is better for us. It keeps everybody interested, it keeps everybody excited, and we again feed off each other. Land speed record is quite unique in that we can be very open with our information, because the way we've solved some problems won't necessarily help Roscoe McLachlan or the Spirit of America team, any of those teams. We've all got very different ways of trying to break the record.
That's going well, actually. That's moved forward quite massively, I would say, in the last year.
Our job with the project is to provide an engine which is going to be the auxiliary power unit for the vehicle, and provide the electronics which are going to drive the engine, some of the control systems and telemetry that's going to get the data off the car into the wider ecosystem for not only the team, but also all the people that are going to be following the program as it starts to run. The engine has not got to run for very long. We've got to pump all the fuel in 20 seconds. So we're moving over a ton of fuel in 20 seconds into the rocket. But the engine is going to be running in an environment that it's never had to do before. We've got all manner of challenges that have got to be addressed before this is going to succeed. And for example, nobody's made an engine like this have to run in a supersonic airflow before. That's just one of the type of challenges that we've got to deal with. Initially we thought, is it just going to be another land speed record? I say just, this is a hell of a challenge. But the aspect of the whole program that I found really engaging was the educational one. Companies like Cosworth require young, motivated, well-trained people to come through and join engineering. They're our lifeblood. And programs like this are just wonderful to engage with people when they're considering what career they want to take, to understand that engineering can be fantastically fun as well as very rewarding, and get them to decide that this is a career choice they want to take. We've used this as a reason to open our doors and show people what we do. I've been completely stunned by the degree of engagement we've seen from both the school kids and their teachers. And the most heartening thing for me is the number of letters we've received from the kids saying, you know what, now we've seen what this is all about, we want to be engineers when we grow up.
This is an engineering adventure aiming to inspire a generation. Taking a wider view than just a record, what are our big societal challenges, whether it's energy or transport or the environment? Actually, the big challenge is none of those things. It's the people who are at school today who will be solving those problems and living in that high technology, low carbon world of the future. How are they going to get inspired about science and engineering and engaged in it when science and engineering is now something that happens inside your iPhone, not something that people actually do? So we're trying to reach out to a whole group with something that you can see and feel and touch and understand. Jet engines and rocket engines and 1,000-mile-an-hour cars run live video from the cockpit direct onto the internet. Technology's never existed before. We can now actually do that. We can put live data straight into the classroom, so while we're doing a turnaround on the desert, the kids can do the same data analysis in science lessons in the classroom. A unique opportunity. Reach out to all those 8 and 10 and 12-year-old kids who one day will create things we haven't even dreamt of. That's the problem we're trying to solve. And the way we're going to do that is to reach the limit of where modern technology will take us, 1,000 miles an hour.